Yeah, sure.
So our next speaker is Rodin, who's going to tell us about high-fidelity metaprogramming with separator syntax trees.
Oh. Yeah, thank you. So yeah, this is joint work with Thijs van der Storm, and we're both at CWI in Amsterdam. So this will be a metaprogramming talk, and just to give you a brief introduction, what is metaprogramming? Well, metaprogramming is the art of writing programs that take source code as their input somehow. So obvious examples are compilers, interpreters, but you can think of obfuscators as well. And what we see is that for a subset of these tasks, in particular tasks that do some, let's say, replacements inside of some source file, so that the source and the target language are the same, which are tasks such as refactoring or automated bug fixing, we see that it's important that these transformations preserve layout as much as possible, as to not make the code look foreign to the developers, even if parts of the code is untouched. And when we are metaprogramming, so these type of code transformations, we call them high fidelity. And if we do metaprogramming, we don't really look at source code as a plain string, but instead we parse it into some sort of syntax tree format, and there are two main flavors in this. So on one hand, we have abstract syntax trees, where we abstract away from non-essential details, such as, well, layout, indentation, but you also won't find comments usually, or, well, operator literals in abstract syntax trees. And these abstract syntax trees usually have a clearly defined structure, usually an algebraic data type underlying them. However, if you want to go back from abstract syntax trees to source code, you have to do some pretty printing, which is, well, not high fidelity. And on the other side of the spectrum, we have concrete syntax trees or parse trees, and such trees do have all the source code in them. However, they usually reflect a production from some formal grammar, and writing such a formal grammar is not fun for a realistic language. And such concrete syntax trees are not widely supported, and even if you have a metaprogramming system that does support them, well, you really need to have concrete syntax patterns to navigate through them easily. And again, you have to write a concrete grammar in the specific grammar formalism of the metaprogramming system you're using. So if we look at rewriting using either formalism, let's look at what a rewrite rule, let's say, in abstract syntax looks like. So this is a rule which has a left-hand side and a right-hand side, and this particular rule tries, well, with this particular rule, we try to find conditionals with a negated condition. So we have an if-then, and the condition has a not, and then there are two branches S1 and S2, and this rule intends to rewrite this to, again, an if statement, but the negation is the condition is no longer negated, and the branches are swapped. Yeah, as you can see, the left-hand side and the right-hand side of this rule are in abstract syntax, and in the context of high-fidelity transformations, that two problems are apparent here. So the left-hand side of this rule is matched against an abstract syntax tree, meaning that the meta variables E, S1, and S2 have no associated layout anymore. And on the other hand, on the right-hand side, we have introduced a new syntax tree, which doesn't have any layout at all. And if we look at rewriting with concrete syntax trees, it looks a little different. I'm going to do a little bit of merchandising here. So all the code fragments here are in Rascal, and Rascal is a metaprogramming environment / language workbench we develop in Amsterdam ourselves. That's it. And this is what concrete syntax patterns look like in Rascal. So again, we have a rewrite rule here, and the top line is a concrete syntax pattern of type statement. So the thing between the parentheses is the type of this thing, and between the backticks, we have our concrete syntax in the object language. And the blue variables between the triangular parentheses are our meta variables, which are typed this time. And again, it's the same rule. Oh, that's a bug there. There should be an exclamation mark at the top line. So again, the rule states the same thing. However, now the right-hand side does have associated layout. So the metaprogrammer here decided that it would be a good idea to write this as a one-liner. But he could as well have defined it like this, where the left-hand side is the same, but now the right-hand side is indented with multiple lines. So what you write down here on the right-hand side does in fact matter. But if you want to do this, you need to have a concrete grammar in Rascal, in this case, like I mentioned. And writing such a grammar is just very error-prone and very laborious. So our goal is to have, so we want to be able to do high-fidelity code transformations without having to rely on concrete syntax patterns. And our solution is that we want to augment abstract syntax with strings that represent pieces of source code that are not really represented in abstract syntax. So just to position it a little bit, what we see is that concrete syntax trees are high fidelity, but they do require a grammar. And on the other hand, abstract syntax trees are low fidelity, but don't require a grammar. And with SSTs, so the separator syntax trees, well, we want to have the best of both worlds. Right, so like I said, it should be lightweight, just like abstract syntax, and we want to be able to unparse it back to source code. So as an example, let's consider a simple expression language. This is our language Exper, at least the abstract syntax of Exper. So we have 5 constructors here. We can define literals, we can put parentheses around other expressions. We have function calls to some function with any number of arguments, and then we have multiplication and addition. Now, as I mentioned before, we want to extend abstract syntax by allowing, by having these constructors supporting a list of strings that represent concrete syntax. So what we do here is that we just add a list of strings to all of the constructor alternatives, but not to the literal one, because we assume that if you merely wrap a string, then that string just represents the concrete syntax of that constructor. So yeah, there's one thing we have to do here. So I mentioned that a function call may have any number of arguments, but of course there's also some syntax separating those arguments. So we need to be able to store strings as well. And to do that, we need a special type of list. So instead of a simple list of expressions, we now wrap this into a generic data type, which we call seplist. And this merely wraps just a list and has support to store strings as well. So by just doing these 2 things, we obtained a separator syntax tree definition for Exper. And if we look at some examples of how separator syntax trees relate to abstract syntax trees, let's look at some examples. So in this case, we have a 1 between parentheses, and the abstract syntax is, as you would expect, a parent node with a literal node with the string 1 in it. Now, if we look at what we're, let's say, missing in the parent node, then we see that the literal 1 here only covers the second character of the concrete syntax. So as our first separator, we need the opening parentheses, and as our second separator, we need the closing parentheses. And indeed, if we make this into a separator syntax tree, then we see that we have added this list containing the 2 strings. And we can also do this for an addition. So if we add 1 and 2, then the abstract syntax is an add node with the two operands as its children. What we see now is that there is nothing in front of the first operand for this addition. There's also nothing after the second operand. But between the 2 operands, we see that there is some white space, and there's the operator plus. So that's what we save as one of the separators of the add node. And now this constitutes the list of separators for this add node. So indeed, there is an empty string in the front, an empty string in the back, and the spaces and the plus in the middle. And as a final example, let's look at a function call. So apparently there is a function f, which we can call with 2 arguments, and there is some inline common there. And the abstract syntax is obviously this. So there's a call node with the function name f, and there is a list of 2 arguments, 1 and 2. Now, if we make this into a separator syntax tree, the first thing we do is we wrap this list of arguments into this. So the comma and the inline comment appear as a separator in this special type of list here. And the call node itself has some separators too. So in this case, we see that there's nothing in front of the function name, so the f. However, there is an opening parenthesis between the function name and the first function argument, and after the final argument, there is, again, a closing parenthesis. So if we add these separators to the call node as well, then we finally get this as our final separator syntax tree for this function call. And there is an implicit invariant popping up here. Well, it's not implicit, but I just didn't put it on the slides. So what we see here is that for every instance of this special list type, the number of separators is equal to the amount of list elements minus 1, or 0 in the case of the empty list. And for all other nodes, we see that the number of separators is equal to the number of children plus 1. So it's and minus 1 for all the separators between the child nodes, and 2 for the surrounding ones. And that is very convenient because, as I mentioned, we want to be able to unparse such trees back to source code. And well, by design or by construction, every node has a seps field, and every list has a seps field containing the separating syntax. And what we can do now is just alternatively print out a separator and yield a child node, and do this until we're done. So I have an example too. So this is the same separator syntax tree we saw before. So if we want to yield this back to source code, then we first print out the opening parenthesis, then we yield to the literal 1, which is 1, and then we print out the final separator, and we obtain the 1 between the parentheses back again as intended. And it also works for the addition here. So this is the addition from the 2 slides ago. Well, we start out with the empty string, then we print out the 1, then we have the spaces and the plus, and the literal 2 and the empty string again. And it also works for the function call, obviously. So if we look at what rewriting would look like in with separator syntax trees, let's consider this rule here. So this is a rule that matches a call node to a function f, and saves the arguments to the meta variable args. And it rewrites it to a function call to the same function f with the same arguments, but it adds some logger argument here. So what we see now is that the left-hand side of this rule is no longer matched against an abstract syntax tree, but it's matched against a separator syntax tree, which means that the args meta variable has associated layout. And that's very useful because how this works is that first we substitute on the right-hand side this args variable by yielding the associated node or list to args. And so we yield the args variable, or well, the value bound to the args variable, and we insert this string into the right-hand side. We parse this into an SST, and again, the layout on the right-hand side is important because it's preserved. And after we parse this, we have a new separator syntax tree, and we can insert it back into the syntax tree we were matching against. So whenever we have a list substitution, we have a problem. So let's consider what happens when we match the left-hand side of this rule to a function called to f with no arguments at all. So if we naively do the sort of algorithm I defined on the previous slide, then we would substitute, we would yield args. Well, args is an empty list now, so the only reasonable thing would be the empty string. But if we naively do that, we end up with this as our replacement syntax, so to say, which, well, is a syntax error. And while we could have decided that the metaprogramming should handle such cases explicitly, we've decided not to do this. We've decided that that the metaprogrammer can, let's say, mark a piece of source code on the right-hand side. So in this case, it's the piece of source code between the section marks here, and the rewriting runtime should detect that the args value is bound the empty list now, and because it is the empty list, it should remove the marked fragment that is adjacent to this meta variable. So if it does that, then we obtain this as our replacement source code, which will nicely parse into a separator syntax tree. All right. How am I on time? All right. So as an evaluation, we implemented separator syntax trees in Rascal with C++ as our object language. And this implementation was based on previous work where we implemented abstract syntax for C++, which in turn depended on Eclipse's C++ tooling. In this case, we chose to use our previous work, which is a concretely framework, allowing us to write concrete patterns on the right-hand side, on the left-hand side as well, because admittedly, abstract syntax looks nice on these small examples, but if you want to write a pattern that is realistic as a refactoring target, then it gets very tedious quickly. So this framework allows us to write concrete syntax patterns on the left-hand side, which are then under the hood transformed into abstract syntax patterns or separator syntax patterns in this case. And what we did was we implemented the encapsulate field refactoring for C++, which intends to transform public member declarations into private member declarations. So just as an example here, consider the C++ class definition here. As you can see, there is a function declaration here, which is not a target of the refactoring, but the variable declaration x here is. And the intention of this refactoring is that we will obtain something that looks like this. So this important comment is preserved here, as is the function declaration, but this part here is new. So visibility is set to private. Then we declare the variable x private, and then we add a public setter and a getter function for this variable. Yeah. If we write this refactoring down in Rascal using separator syntax trees, it looks a bit different. So this is now the left-hand side of my rule. So what we see here is we have a concrete pattern of type decl, which is a class declaration with a public visibility label and then a member declaration. And well, there could be an arbitrary number of declarations before, after, and in between these two. So we store them in meta variables. And if this pattern matches against a separator syntax tree, all these variables are bound. And what we do here is we write a new, well, we define the new class definition. So what we see here is that the pre, and between, and the post variable appear again. But now we have this visibility label, and we have a new declaration here for the now private member variable, and we also add the getter and the setter function where the name is capitalized first because people want camel case. And this interpolation here on the right-hand side is just a variant of Raskell's interpolation. So this all works fine, and it automatically is transformed into, it's automatically yielded into a string. And finally, we parse this new class declaration and insert it back into the tree. So there are some limitations here. So because this is all mapped back to a string and then parsed, it's possible that you capture some operator precedence that you do not want. So the indentation strategy is currently not optimal, so at least it can be improved. And what we see is that we parse the full pattern, the full right-hand side pattern on every time that the left-hand side matches against the tree, which is unnecessary. So we can improve that by doing some compile time parsing. So I'll conclude here. I introduced separator syntax trees to you, which are lightweight like ASTs, but high fidelity like parse trees. And if you're interested, then please read the paper. So thank you for your attention.
Thanks. Interesting work. My question was going to be the 3 limitations that you had on there.
Yeah.
How you were going to deal with that. So it seems that they are limitations. So have you thought about how to deal with that? And a related question is also, how do some of the related work on this, so for example, Coccinelle must deal with this problem somehow? How do they deal with stuff like this?
Right. So, well, I'd say the textbook solution to the first one is to just add parentheses, but then you end up with possibly redundant parentheses, which you might be able to solve if you add another rewrite that detects a parenthesis around, well, let's say a constant, or well, you could, I guess, detect it by using your knowledge of the operator precedence of your abstract trees, or separator syntax trees. Indentation, yeah, we can be a little more smart. I'm not sure whether we can solve everything, but it can be improved at least. And the repeated parsing, well, we can do that if we're able to introduce, let's say, placeholders for the meta variables, and then parse the whole right-hand side of a pattern at compile time, and then fiddle in the actual values bound to the meta variables at runtime. Yeah, I can't say I'm sure how Coccinelle does some of these things, to be honest.
So I want to understand your purpose. If you want to just say implement refactoring, just want to keep the layout, then this method seems you need to define a nice language for describe layout. Actually, just now you have several things, have space there, and later will be filled in. And another way is people do using bidirectional transformation. While we have a concrete syntax tree here, while I have abstract syntax tree here, you do right transformation just over abstract syntax tree, do refactoring. But because synchronization between a concrete syntax tree and abstract syntax tree, you could keep quite a lot of layout in the source in the concrete syntax tree, where you can still have some same effect as you like, as you just printed here. Have you thought about this kind of comparison with that kind of approach?
So I guess that presupposes that there exists a grammar in the formalism of the system you're using, and that's explicitly not what we're assuming. So we want to be able to do this without having to define a grammar. So we live in a world where there are no concrete syntax trees, so to say. So yeah, keeping this...
Right. This is another approach. Yeah, another approach. Quite a lot of people actually work on that. Seems to try to do this kind of keep the layouts, keep all the things.
Yep.
Yeah, because I think this is quite flexible because you can describe many things, right? Your transformations, concrete syntax go to abstract syntax go to concrete syntax. This is quite nice, but this depends how people use that.
Yes.
Yeah, okay. Yeah, great.
There's one very quick question. If not, we'll go to the break. Okay. Let's take Rodin again.
Thank you.